Hello and welcome to our fifth episode of Escape Velocity Space News. Getting to the fifth show isn't a major milestone for a lot of television shows, but this isn't every show. What you're seeing right now is a not-for-profit, free-to-air science show that is funded through Patreon. This means that everyday people just like you said, I want more science in my life. And this is the team I'm going to support to bring me that science. As far as I've been able to tell, we're the first crowd-funded network show. And this means I can talk to you about climate change, about astrobiology, about the good and the bad of different rockets, and not worry about advertisers pulling their support. I get to be a science journalist with just one concern. Can I put more science in your brain? And getting to 5 episodes, to me and to our director, Ali Pelfrey, and to everyone else on our team, means a lot. And I just want to say thank you to everyone who has supported us so far. And invite all of you who are either new or who didn't know we have a Patreon, come join us. Get extra content, get extra access. And get more science over at patreon.com/CosmoQuestX. CosmoQuest? That's our production group, like Bad Robot, but less famous. And that X, that marks where the science is. This week, thanks to the support of so many, we're going to be looking at earthquakes, early results from the JWST, spherical novae, the dark side of the moon, and a whole lot more. I am Dr. Pamela Gay, and I am here, thanks to you, to put science in your brain. One of the most difficult to understand parts of any world is the story of its surface. We look to Venus and see a world with essentially no craters, and this tells us its surface is young and either has constantly renewed itself through the rumbling of volcanoes, or its entire surface was remodeled in a tremendous upheaval of planet-wide eruptions. What happened exactly? Can't tell. Not sure. We look to Mars, and we see tremendous volcanoes and a gaping valley that might have split open as eruptions elsewhere grew the largest mountains in the solar system. We thought that volcanoes and quakes on Mars were a thing of the past, but the InSight mission has taught us that eruptions are still happening, and there is still magma inside Mars. How can that be? No idea. And then there is Pluto, which somehow has mountains formed of ice the same way mountains form through plate tectonics here on Earth. The geologically interesting worlds of our solar system, whether they be planets or moons or asteroids, they are fundamentally shaped by heat and by the way that heat moves through their surfaces, cracks their crusts, and vomits out ice or lava through their volcanoes. And Earth has a larger molten reserve than any other terrestrial world. This liquid allows our planet's crust to float, and it is made of different pieces that each move independently of the roiling melted rock beneath. When I first started teaching astronomy, I learned you can model these motions using Oreo cookies. We have the plates that are moving apart, and in the gap, new landforms. There are the places where plates are colliding, and that's where we have new mountains like the Himalayas growing tall. And there are the places where the plates ride side by side trying to shift past each other. About 80% of earthquakes are associated with colliding or convergent plate boundaries. And the strength of those earthquakes is related to how much pressure is able to build up before the plates finally give way. The massive 7.8 magnitude earthquake in Turkey and Syria occurred where the Arabian plate is colliding with the Anatolian plate. And this fault, the East Anatolian fault, is under pressure from the African plate as well. This triple collision region has experienced major quakes at various points along the fault, but pressure has been building, with the North Anatolian fault experiencing numerous large earthquakes, while the East Anatolian fault has seemingly been stuck in place, stuck until February 6th. The land was literally ripped open by movement along the fault. And while massive aftershocks continue to release the energy built up along this fault, it is hard not to wonder if this kind of a quake, or perhaps one even larger, is likely to strike here in North America. Two of the largest recorded earthquakes in history have occurred in Alaska: the 1965 Rat Islands quake at magnitude 8.7, and the 1964 Prince William Sound quake at magnitude 9.2. Both quakes also generated tsunamis, but the overall toll of death and damage was minimal due to the low population in these regions. The famous 1906 San Francisco earthquake is estimated to have been magnitude 7.9, and the New Madrid Fault earthquake of 1811 was somewhere between 7.2 and 8.2 magnitudes and changed the course of the Mississippi River. Both these faults continue to rumble, releasing some energy as plates slide. But both are expected to eventually jump forward, and there is no real way to know if that jump will be tonight or 100 years from now. And if you want to give yourself nightmares, read up on the January 1700 earthquake in Cascadia that had a magnitude between 8.7 and 9.2. and generated a tsunami that was measured in Japan. We have fault lines. What happened in Turkey could happen here. Where exactly it could happen? It turns out it all comes down to composition. A new paper in the journal Science, led by UT Austin researchers Srisharan Sridharan and Demian Safar, shows that the ability for material to break apart and bond back together, or not, ultimately defines how future quakes will occur. In some areas, the rocks and minerals that make up the plates are like an Oreo cookie, rather crumbly. It doesn't take a lot of energy to make the plates shift, and just like the cookie crumbles, the clays along the fault don't bond back together to harden the landscape. This is the case along the Hukaran-Gi Fault in New Zealand, which undergoes regular small earthquakes, just as this team's samples of fault materials predicted. Where the landscape is able to cement itself back together under pressure, energy can build up instead, and massive slips are more likely to occur. Unfortunately, we don't have samples of the material making up most fault lines, but we can get samples if we have the will and the funding. As Safar explains, quote, "With the right samples and field observations, we can now start to make testable predictions about how big and how often large seismic slip events might occur on other major faults, like Cascadia in the Pacific Northwest." End quote. This new technique won't tell us when the big one is coming, but it gets us one step closer to understanding where to watch and tells us what to measure. This new study provides a framework for placing sensors along key areas of faults. This is a start, and as someone living in the shadow of the New Madrid Fault, I'll take any data we can get. We don't need to fear our Earth. We need to understand it and prepare for all the weird and wonderful and sometimes gross things it has to throw at us. While I'm now a Midwesterner, I was actually born in California, and I remember getting tar on my feet as a small child looking for seashells along the Malibu beaches. That sticky beach tar was a side effect of all the petroleum near and at the surface in that region. Where Los Angeles has the La Brea tar pits, further up the coast, tar erupts out of the sea floor. Like I said, our world can be gross. Oil seeps aren't entirely uncommon. According to NOAA, roughly half the oil released into the ocean each year comes from naturally occurring oil seeps that basically ooze out tarry crud. In just a handful of places, however, something different occurs. Instead of seeps, there are asphalt volcanoes that erupt with tar and can grow to be well over 50 feet tall. Two of these asphalt volcanoes are in the Santa Barbara Channel. Remarkably, these volcanoes are teeming with life, and a new paper in the Bulletin of Marine Sciences details how life can adapt to survive this sticky situation. This work was led by UC Santa Barbara's Milton Love. His team used an autonomous underwater vehicle to capture 8 hours of data, 2,743 still images in total, to document 43 species of fish, as well as numerous invertebrates they hope to document in a future paper. While the aspects of both surface-level oil seeps and deep-sea oil release from wells and pipes are consistently devastating, these sticky mounds are proof that, given time and the ability to adapt, life will find a way to live just about anywhere. After the break, we'll be back to look at stars, star formation, and the perfect explosions some stars create. The last week of February, the astrophysical journal Letters released a special issue covering the latest science results from JWST's first images. These 50-plus papers each look at different early images taken by JWST while it tested its equipment, and these papers allow researchers to see that yes, JWST is working and is capable of doing the science we've been waiting for. A lot of this research is just a taste of what is yet to come, but I'd like to try and give you a rundown of what we are literally seeing with JWST. And here is where I get to say one of my favorite random sets of words: polycyclic aromatic hydrocarbons. These complex organic molecules are things we have on Earth, and they form during the burning of coal, tobacco, garbage, even meat. Basically, burn something rich in carbon and get polycyclic aromatic hydrocarbons. And space is oddly full of polycyclic aromatic hydrocarbons, and JWST studied them in its first set of images. These molecules absorb and emit bands of light in the infrared, and JWST has filters to catch the light associated with these vibrational transitions. These molecules grow very slowly in cold, diffuse gas in the spaces between stars. The polycyclic aromatic hydrocarbons emission is extremely faint, but with JWST's large mirror, the emission is enough to allow researchers to take a census of the cold gas in nearby galaxies. And there are some who describe what JWST is seeing as lace or Swiss cheese, or one researcher joked on Twitter that it looked a bit like an eldritch horror. Can't disagree. The network of voids and walls of gas traces temperature variations and density variations. Hot stars heat the gas and shatter fragile molecules. For now, within this dust, researchers are finding the start of star cluster formation, with dozens of potential clusters younger than 2 million years lurking in this web of gas. One of JWST's raison d'etre is providing the images we need to understand star formation. Knowing that young clusters hide inside cold gas clouds, That is one new piece of the puzzle. But it's not the only piece we get in this special issue. Looking at the nearby spiral galaxy M74, researchers find star formation distributed all throughout the galaxy's arms, which is expected. What was less expected is they also find star formation in spurs of gas off the arms that hasn't had time to travel there and must have actually started there. Spiral galaxies are weird to think about. What we see as grand design spiral structures is just a pattern generated through gravity and time. Each star that we see in an arm is simply passing through as it orbits. But because there is so much mass in the arms, the stars will first accelerate into the arms as they approach, and then leave only slowly. What we see as arms are a reflection of stellar traffic jams where everything just slows down and piles up for a time. And that piling up part, when it is gas instead of stars, the piling up can trigger star formation. But the gas in the spurs forms on the wrong time scales for that enter an arm form stars story to explain what we're seeing. Apparently, now we know, stars can also form in spurs. JWST's giant mirror is the key to seeing both faint features and small details. Side-by-side comparisons of JWST images and similar images taken with the much smaller Spitzer Space Telescope look like an enhance button was made to clear up details in the universe like they were evidence in some TV cop drama. Karen Sandstrom, one of the myriad researchers with work coming out, puts it this way, quote, "With JWST, you can make incredible maps of nearby galaxies at very high resolution that provide amazingly detailed images of the interstellar medium. One of the things I'm most excited about is now that we have this high-resolution tracer of the interstellar medium, we can map all kinds of things, including the structure of the diffuse gas, which has become denser and molecular for star formation to occur. We can also map the gas surrounding newly formed stars where there is a lot of feedback, such as from supernova explosions. We really get to see the whole cycle of the interstellar medium in a lot of detail. That is the core of how a galaxy is going to form stars." End quote. With our eyes, we see the hot light of stars and the emission of heated up hydrogen and oxygen and other often ionized gases. With JWST, it's all cool and it's new, and we are about to learn so much. But I have to admit, my heart belongs to the higher energy parts of the electromagnetic spectrum. It's in gamma and X-ray light that we see dramatic explosions and superheated gases. It's in ultraviolet and optical that we see the hottest young stars and the remnants of dying stars. Back in 2017, a pair of super dense dead stars, neutron stars to be specific, were caught in the act of merging. They gave off a blast of gravitational waves that were detected by LIGO and Virgo, and they screamed out light that was spotted by the Fermi and Integral X-ray observatories. As the explosion and merger progressed, we began to see optical emission and even radio emission as the system expanded and cooled and its shock wave propagated through the surrounding gas. We now call neutron star mergers kilonova, and we're starting to understand they may be the source of the majority of the gold in the universe. Researchers are trying to model exactly how the merger takes place, and we're now realizing those models are wrong on one very key factor: the shape of the explosion. From analysis of observations, we now know kilonova explosions are spherical. This work is published in the journal Nature with lead author Albert Sneppen, who is a student at the Niels Bohr Institute. Sneppen explains, quote, You have two super compact stars that orbit each other 100 times a second before collapsing. Our intuition and all previous models say that the explosion cloud created by the collision must have a flattened and rather asymmetrical shape. End quote. Human intuition wasn't designed to handle neutron star mergers, however. Sneppen further explains, quote, "The most likely way to make the explosion spherical is if a huge amount of energy blows out from the center of the explosion and smooths out a shape that would otherwise be asymmetrical. So the spherical shape tells us that there is probably a lot of energy in the core of the collision, which was unforeseen." End quote. This spherical shape has some real cool consequences. If we see light coming at us from an unsymmetrical object, we can't know how much of the object's light we're getting unless we somehow know its orientation. With extremely distant objects, they all look like points, and we just can't know what's going on. If something is spherical, the same amount of light is given off in all directions. Sneppen's advisor, Darach Watson, adds, quote, "If they are bright and mostly spherical, and if we know how far away they are, we can use kilonovae as a new way to measure the distance independently, a new kind of cosmic ruler." We don't really know how common kilonovae are, but this is potentially one new tool we have to measure the size of our universe. Sometimes the universe hands you an eldritch horror of a galaxy. And sometimes it hands you the perfect sphere. After the break, we'll be back to take a closer look at the electromagnetic spectrum. And this segment is totally inspired by the 50th anniversary of Pink Floyd's Dark Side of the Moon. Stay tuned. At the top of the episode, I said we'd be taking a look at the dark side of the moon. And I'm betting most of you thought I'd be talking about this, the far side of the moon. No. I wanted to take a moment to pay tribute to one of the best out of context science references in pop culture, Pink Floyd's The Dark Side of the Moon. Released on March 1st, 1973, this album just turned 50. And as a former physics professor, I want to take this moment to say thank you to the remaining members of Pink Floyd for providing me with so many cool ways to help my students learn science. Let's start with that name, Dark Side of the Moon. First of all, the moon doesn't have a side that is constantly dark. Half of the moon's sphere is always illuminated, and as the moon goes around the Earth, it always keeps the same side facing us while constantly changing what it is showing the sun. When you see the thinnest crescent moon in the sky, the rest of its disk is that moment's dark side of the moon. I've often wondered why the far side got called the dark side. I guess in the ignorance of not knowing what was there, someone thought dark was a pretty good word to use. It fits with how we name dark matter, dark energy. Yeah, we really shouldn't be allowed to name things. In 1959, humanity got its first glance at the far side of the moon when the Soviet Luna 3 beamed back images to a Crimean mountaintop radio dish. These images were recorded on film that had been confiscated from a crashed U.S. spy plane, a U-2 spy plane, just in case you needed another pop culture reference. Luna 3's images and subsequent missions revealed the moon's far side as a geologically different place with more craters, fewer dark lava features, and literally a different texture from what we're used to. And that far side, it's actually on average lighter than the near side. It's not the dark side. It might be the bright side. And it's illuminated just as often as the side we see. The Dark Side of the Moon is a great title for an album, and it is just further evidence really, astronomers should never get to name anything. That 50-year-old album, in addition to its sciencey name, also had on its cover a depiction of light passing through a prism and getting refracted. The only thing the cover and the name have in common is they are both science references. But I am here for the science. Here's what's happening in that image. The light, like a sunbeam, appears white because it contains photons, light beams, of every single color. As the white appearing light enters the prism, it bends, with different colors bending different amounts. The aspect of light that gives it the color we perceive is the wavelength of light, which is related to its energy. Red light has a longer wavelength and less energy. It enters, bends a bit, and carries on as it goes. As colors move through the rainbow, red, orange, yellow, green, blue, indigo, violet, the wavelengths get shorter, and the amount the light bends increases. And ultimately, that rainbow we see is just a sorting of light by energy. The same kind of bending, technically called refraction, happens when light moves through any substance, and it's why we can make rainbows with raindrops, prisms, and the occasional water glass. The thing is, not all the colors of light are visible to the eye. This was learned quite by accident by conductor, oboist, and all-around astronomy lover William Herschel. He was a pioneer in astronomy because he, like many amateur astronomers today, learned to make his own telescopes and explored the skies. What ultimately made him the Astronomer Royal of England was his dedication to writing down and reporting on what he saw. One of Herschel's studies included trying to measure how different colors of light heated up their surroundings. He did this with careful controls, and it was really a beautiful experiment that made it clear that redder colors were more effective at raising temperatures. And then something weird happened. As he was working and the world was rotating, the rainbow of light he was studying shifted so that the rainbow of light was beside his thermometer, with the red just beyond the temperature bulb. Remarkably, the thermometer temperature showed a hotter reading than it had for any of the colors of light he could see. This led Herschel to realize light comes in colors we can't see, and light beyond red, what we now call infrared, is perceived as warmth or heat. It would take a full understanding of how light and heat and energy are all related, but don't always move in the same ways, to piece together all the things Herschel discovered that day. It turns out blue is far more energetic, even if his thermometer didn't measure that. Infrared isn't the only color that lies beyond what our eyes see. Going to the red, we go to infrared, microwave, millimeter, radio. Longer and longer wavelengths as we go. Toward the blue, we get to ultraviolet, X-rays, gamma rays. Light, which is carried by photons, is unconcerned with the limits of our eyes, and it is just interested in carrying energy as it goes. To fully understand our universe, we have to explore our sky in every single color of light. Each color tells a different story, with high-energy photons coming from high-energy interactions or high-density gases. Infrared and longer wavelengths tell us the stories of molecules, and some colors, like the shades of radio seen in galaxy jets, come from electrons and other particles twisting in fields. Every color has its own stories, its own sources, and its own science. And to see all these colors, we need a suite of observatories. Here on our Earth, we can effectively see most colors of radio light. If we couldn't, ham radios and car radios and other radios really wouldn't work. In the 1900s, ever larger radio observatories were built, with the two great systems in the US being Arecibo with its massive single dish that went live in 1963, and the Very Large Array with its myriad disks spread over an even larger area that was constructed between 1973 and 1980. Infrared light and the shorter wavelengths of ultraviolet, X-ray, and gamma ray are all blocked to varying degrees by our atmosphere. And optical light is blurred by our atmosphere. To escape the problems of air, NASA launched its 4 great observatories between 1990 and 2003. These included the Hubble with its ability to see from the near infrared through to the ultraviolet, the Compton Gamma Ray Observatory, the Chandra X-ray Observatory, and the Spitzer Space Telescope. Together, these facilities made it possible for folks like me to understand the universe from a variety of different perspectives. In college, I used radio surveys to find clusters of galaxies, and I looked for X-ray light to hint at their mass and measured their optical light to get at their distances. It takes every color of light to understand our universe. Today, we have the Fermi Space Telescope capturing the gamma rays and JWST looking in the infrared. And there is a remarkable team at Chandra who work to bring together images from all these teams to allow us to see our universe. Their false color images let us see how jets leap out of spiral galaxies. They let us see how galaxies spill out their gas as they enter galaxy clusters. They reveal jets from stars and from galaxies. And they make pulsars stand out from all the other bright stars. That album cover, it is a gateway to all of astronomy, a rainbow formed by light through a prism. That's how infrared astronomy started. And that's how we learned light was so much more than our eye can see. So go out. Ask someone if they know that the dark side of the moon is only 50 years old. And talk about our moon that doesn't have a dark side. And tell them about that prism and all the telescopes that prism led us to create. Oh, and one final thing. There has been this weird thing on the internet with people saying Pink Floyd is way too woke with their updated album art for the 50th anniversary edition. Folks, that's just the prism displayed in a new and interesting way. It's all just science. Oh, and this isn't science, but the album, it really does weirdly line up with the action in The Wizard of Oz. Start a record on the lion's third roar and see it for yourself. Up next, we're going to talk more art and science, and also bring back Eric Mattis to talk rockets. Stay tuned. Science is a habit of looking at things and sometimes going, yeah, that thing you thought was just art, we're going to show how it can be useful for science. In a completely unexpected turn, researchers studying the Impressionist movement have pieced together that the diffused light, blurred edges, and overall haze of Impressionist paintings is a reflection of the significant air pollution of the Industrial Revolution. Throughout the 1800s, coal powered the mills and factories in Europe and North America, and it was also used for home heating and cooking. At the end of the 1800s and moving into the early 1900s, efforts to reduce air pollution led to a switch to gas in homes and efforts to mitigate factory pollution. The rise and fall of coal-burning tracks with both the rise and fall of the Impressionist painting style, and atmospheric sulfur dioxide. While correlation doesn't necessarily mean causation, in this case, the relationship seems real. Researchers Anna Lee Albright and Peter Hubers quantified the color contrast in works by British artist Joseph Turner, whose work spans from 1790 to 1851, and Claude Monet, whose work spans from 1851 to the early 1920s. Both artists painted land and cityscapes and were exceedingly prolific. In both cases, contrast rose and fell with sulfur dioxide levels. As light passes through atmospheric sulfur dioxide, it gets scattered, much like light passing through fog. This has an overall effect of decreasing color contrast and softening edges. In their analysis, Albright and Hubers used photographs obtained during clear skies and polluted skies to quantify how pollution affects contrast. They used the same relationship to study contrast in Turner and Monet's paintings. This same relationship was also reflected in works by other Impressionist painters. Consistently, the contrast trended with sulfur dioxide levels more than with time. This research gives me very mixed emotions. I have to admit, I love Impressionist art. But the idea that this artistic movement is defined by severe pollution, that's just a little heartbreaking. I guess this is a case of the artists, or at least their lungs and eyes, truly suffering for their art. It shouldn't be surprising that we can use art to understand our Earth. The greatest artists have always been fine observers of the world around them, with details of anatomy and motions and perspective all finding their way into paintings and sculptures. And one artist's careful observations almost got us an understanding of gravity more than 100 years before Galileo developed his laws of motion and inertia. That artist was Leonardo da Vinci. Caltech's Maury Garib was reviewing Da Vinci's work on flow dynamics when he spotted notes on how small bits, sand or drops of water, fall from a tipped vase that is sliding. Da Vinci realized that the falling bits aren't moving at a constant rate, but instead are accelerating. Without the aid of a stopwatch or any other way of accurately measuring time, Da Vinci didn't quite get the right relationship. He came up with the acceleration being related to 2 raised to the power of time. In reality, the rate at which an object falls is related to time squared. The relationships are close, and it is amazing to imagine what might have been if Da Vinci only had an accurate watch and calculus. Newton would have to independently create calculus as part of coming up with his understanding of gravity and motion. And thanks to Newton and the relativistic corrections added by Einstein, today we can launch rockets. And there are oh so very many rockets getting launched. Hey Eric, what is the latest in the Russian capsule saga?
Thanks, Pamela. Soyuz MS-23, the capsule launched to replace the damaged Soyuz MS-22, successfully launched to the ISS on February 24th. A few hours after launch, it docked with the ISS. Instead of the usual welcome ceremony, the crew that would ride it home swiftly moved their seat liners from the old spacecraft to the new one. The seat liners are molded during training to the shape of the astronaut that uses them and act as extra padding on the return trip, as the landing of the Soyuz spacecraft is quite violent. Soyuz MS-23 will not immediately return to Earth, however. It will spend the standard 180 days attached to the station, barring any other problems. This means that the crew of Russia's Sergei Prokofiev and Dmitry Butelin and NASA's Frank Rubio will spend a year in space. Soyuz MS-22 will return to Earth without a crew later in March, carrying some supplies. Roscosmos will inspect it for damage after it returns. Staying with human spaceflight for a moment, big SpaceX news this week was the launch of Crew 6 in the wee hours of Thursday, March 2nd. This mission was a major milestone in many ways, including it's the 8th flight of the Crew Dragon, and the spacecraft has already carried more people into space than NASA's Gemini program. One more flight and it will exceed the number of people sent into space by the Apollo program. This was actually the second attempt to launch Crew 6, following an attempt a few days earlier that was scrubbed just a couple of minutes before T0 due to a problem with some of the ground support equipment. Crew 6 is the last of SpaceX's first contract with NASA to send crews to the ISS. They are currently contracted for a further 8 flights under 2 contracts between now and 2030. These flights will see the ISS through to its retirement, at least under current plans. The composition of Crew 6 follows the pattern seen on previous flights of one experienced astronaut and several rookies. The veteran this time is NASA astronaut Stephen Bowen, who is on his 4th flight. His previous 3 were all on the space shuttle. On his last shuttle flight, he became the first person to fly consecutive shuttle missions with STS-132 and 133. The other astronauts are Roscosmos cosmonaut Andrei Fedyaev, United Arab Emirates astronaut Sultan Al-Nayati, and NASA astronaut Warren Hoberg. Andrei Fedyaev was selected to be a cosmonaut in 2014. Al-Nayati is the first Emirati astronaut to fly on an American spacecraft. Before being selected as a NASA astronaut in 2020, Warren Hoberg was an assistant professor at MIT. As of when we're recording this episode, they are still on their way to the ISS, where they're expected to arrive after about a day in transit. They will spend 6 months on the ISS performing work from life science to materials research and even some high school student research. You can read more about the research the crew will be doing at a link in our show notes. Like usual, there have been a lot of other SpaceX launches in the last couple of weeks. On February 18th, SpaceX launched the Inmarsat I-6 Flight 2 for Inmarsat on February 18th. Inmarsat I-6 Flight 2 is a huge 5.4 metric ton communication satellite that uses electric propulsion. Unlike previous Inmarsat satellite, it includes both a Ka and L-band payload, with most of the satellite dedicated to L-band. This one satellite has twice the L-band capacity of the entire 4 satellite generation that came before it, and it's the second of 2 in this generation of satellite. The key advantage of L-band is that it allows for low-power transmitters, such as those on airplanes, ships, and various small internet-connected devices, the so-called Internet of Things. The first one, which provides coverage over the Indian Ocean, was launched by a Japanese rocket in 2021. I-6 Flight 2 will provide similar coverage over the Atlantic. The booster successfully landed, marking SpaceX's 11th so far this year. And finally, among the other launches in the past 2 weeks were 4 Starlink missions, launching a total of 178 satellites into orbit for the company's internet constellation. All of the Falcon 9 boosters landed successfully, bringing the number of Falcon 9 booster landings since they entered service to 174. And now for some statistics for a few of the things that are in orbit around the Earth. There are 11 toilets in space, 4 on the ISS, 2 on the Tiangong space station, 1 on Shenzhou 14, 1 soon to be returned to Earth on Soyuz MS-22, 1 on Soyuz MS-23, 1 on Crew Dragon Freedom, and 1 on Crew Dragon Endeavour. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, so far this year, the USA has had 16 launches, China 7, Kazakhstan 3, and India, Japan, and the United Kingdom have each had 1. Of these 28 launches, there have been 2 failures, reminding us that space is hard.
Thanks, Eric. Looking ahead to future missions, the Viper rover is on track to launch in late 2024 on a Falcon Heavy, and to then explore the moon's southern pole region for roughly 100 days. As the TV show For All Mankind leveraged in its plot, these regions may contain reserves of accessible water ice, and Viper is on a mission to find that ice. It still isn't decided exactly where Viper will land, but one possibility is a lunar mesa or flat topped mountain that is roughly the size of Delaware. Standing roughly 20,000 feet higher than its surroundings, this mesa is an ancient feature that, until recently, didn't have a name. On February 15th, as part of Black History Month, NASA shared that the International Astronomical Union has approved naming this mesa Mons Mouton, after NASA mathematician and programmer Melba Roy Mouton. Hired in 1959, Mouton headed the team tracking satellites Echo 1 and Echo 2. In 1961, Mouton became the head programmer for the Mission and Trajectory Analysis Division's Program Systems Branch. The team who coded computer programs used to calculate spacecraft locations and trajectories, giving NASA the ability to track spacecraft while in orbit. According to Acting Associate Administrator for Science at NASA, Sandra Connolly, quote, "She not only helped NASA take the lead in exploring the unknown in air and space, but she also charted a path for other women and people of color to pursue careers and lead cutting-edge science at NASA." End quote. Viper is exploring the path for NASA's return of humans to the moon, and in the next decade, the first woman and person of color to visit the moon just might stand on this mountain thanks to software that has Melba Mouton in its legacy. There will be a full moon on March 7, and this mountain will be visible. Good night, and remember, go out and look up.